Hi students, as you know, NDA has introduced a new unit in the chemistry syllabus for both the NEET and JEE from the year 2024 onwards. The new unit included is the principles related to practical chemistry. Since it is a newly introduced topic, the necessary study materials may not be available in print and visual media. But you need not worry. I am uploading video classes through my YouTube channel explaining the theory related to chemistry practical, which include a lot of multiple choice questions and their well explained answers. By the way, I am Dr. Syriac Matthew, a retired associate professor in chemistry. The purpose of my channel, Chemistry Master, is to upload video classes related to topics in chemistry within secondary, undergraduate, and postgraduate levels. At present, I am uploading video classes related to NEET, JEE Main and Advanced, and other entrance examinations. There will be a set of video classes for each chapter. In the present set of videos, we discuss the principles related to practical chemistry. This set includes 6 video classes. The first one, titled as Principles Related to Practical Chemistry, Part 1A, explained detection of extra elements and detection of functional groups. The second, titled as Principles Related to Practical Chemistry, Part 1B, contains multiple choice questions related to Part 1A. Part 2 explains preparation of some organic and inorganic compounds and a titrimetric analysis. Part 3, qualitative analysis for anions, and Part 4, qualitative analysis for cations. The Part 5 explains some physical chemistry experiments. At the end of each part, multiple choice questions related to that part are explained. Even if you go through a handbook of chemistry practical several times, you may not be able to remember the experiments and the theory behind it. But an audiovisual presentation will catch your attention. That is why I have introduced a lot of animations in these video classes so that you will get a feel of doing the experiments in the laboratory. However, animations never represent the real situation. And this is not an instruction manual for doing the experiments in the lab. The main purpose is to make you understand the theory behind the experiments. In the laboratory, you have to take several precautionary measures while doing the experiments. For your convenience, I have introduced video chapters or timestamps in the description part of the videos. This will help you to watch and rewatch separately the different topics explained in a particular video. The links for other videos are also given in the description part. You can easily move to any of these 6 videos using these links. I hope these video classes will definitely help you to understand the theory behind the experiments. If you like the video, please subscribe my channel and forward to others. You can expect similar video classes from other chapters of Class 11 and Class 12 Chemistry soon. This is part 4 of the 6 video classes on principles related to practical chemistry. In this video, we study about the theory behind the analysis of cations. We need to study the principles behind the detection of the following cations only: lead 2 plus, copper 2 plus, aluminum 3 plus, iron 3 plus, zinc 2 plus, nickel 2 plus, calcium 2 plus, barium 2 plus, magnesium 2 plus, and ammonium plus. 2 important principles used in systematic qualitative analysis are the solubility product principle and the common ion effect. When any product of a salt exceeds solubility product, precipitation of salt occurs. Ionic product of a salt can be controlled by a common ion. It is called a common ion effect. I have explained in details the principles related to precipitation of ions in part 3 of this series of video classes. The systematic analysis of inorganic salts involve the following steps. 1. Preliminary examination using easily perceptible changes such as smell and sight. Determination of anions using reactions carried out in solution followed by confirmatory tests. Third one, determination of cations using reactions carried out in solution followed by confirmatory tests. Let us start with a preliminary examination for finding the cations. Flame test is an important preliminary test for getting indication of certain cations. Chlorides as a metal, especially alkali metals and alkaline earth metals, impart characteristic colors to the Bunsen flame. Since chlorides are most volatile, salts of such metals are mixed with concentrated HCl and introduced into the flame. A small amount of the sample is made into a paste with a few drops of concentrated HCl and introduced into the flame using a platinum loop. As example, let us consider a salt containing copper ions. We take a little of the copper salt in a watch glass and using concentrated HCl we make a paste, and this is the platinum loop, and we introduce a small quantity of this paste into the blue flame. Now the color of the flame changes, a green flame with a blue center. Now we use a cobalt glass to view the flame. We observe the same color, that is a green flame with a blue center. Thus for copper ions, if we view using our naked eyes, green flame with a blue center, and through cobalt blue glass we observe the same color. Concentrated HCl is preferred for making paste. This is because chlorides of these metals are most volatile, so other acids are not used. We can observe the flame with our naked eyes or through cobalt glass. Color observed may be same or different. Cobalt blue glass is used as a filter. The samples used for flame test very often contain sodium ions as impurity. It imparts yellow color to the flame so that actual color is masked. Cobalt blue glass filter out the yellow color. Second example is strontium ions. A little of the salt is made into a paste using concentrated HCl and introduced into the non-luminous flame. And see the change of color of the flame. And this color is crimson red. That is an intense red color. Let us view the flame through cobalt blue glass. Now the color changes to purple. So for strontium ions, when we observe the flame using naked eyes, it appears as crimson red flame. And through the cobalt blue glass, it appears as purple flame. Now consider salts containing barium ions. As before, a small amount of the sample is made into a paste with a few drops of concentrated HCl and introduced into the non-luminous flame using a platinum loop. And this color is called apple green or grassy green. Now we observe the same flame through a cobalt glass. The color changes to bluish green. So with our naked eyes, barium ions give apple green flame or grassy green flame. Through cobalt blue glass, the color changes to bluish green. Once again, I remind you, animations may not be able to generate the true laboratory observations. Very often, it will be different from the actual. Now let us consider calcium ions. As before, a little of the calcium salt is made into a paste using concentrated HCl. A small part of the paste is introduced into the non-luminous flame using a platinum loop. the color of the flame changes. And this color is called brick red color. Now we observe the same flame using cobalt blue glass. The color changes to green. With our naked eyes, the flame appears as brick red. And when observed through cobalt blue glass, it appears as a green flame. Using a table, we can write down all these observations. And using our naked eye, cobalt blue glass, the particular ion that is indicated. If the flame is green with a blue center, and when observed through cobalt blue glass, we get the same color, then the ion that is indicated is copper 2+. With the naked eyes, if it is crimson red, and through cobalt blue glass, if it appears as purple, and that indicates strontium ions. Similarly, apple green and a bluish green indicate barium 2+ ions, brick red and a green calcium 2+ ions. Another important preliminary test is the borax bead test. Borax bead test is performed for colored salts. It is based on the formation of colored metaborates when salts of copper, iron, nickel, etc. are fused with borax. This is borax. From the color of the bead formed, we can identify the cation. When borax is fused and cooled, clear glass result. When such glasses are fused with the salts of certain colored cation, they form metaborates of the respective metals which dissolve in the glasses to give characteristically colored beads. So this is borax, and this is, suppose we take copper sulfate or copper salt. Now we take some of the borax using a loop and introduce into the non-luminous flame. The yellow color is due to the sodium ions present. Now this is converted to the glassy material. And we now dip that glass bead into the copper salt. And we again heat it in the non-luminous flame. When it is cooled, the color changes. For copper salt, we get a green bead. This may not match with the experimental observations, actual experimental observations. Now, copper sulfate reacts with the borax and a copper metaborate is formed. When heated in non-luminous flame, the color of the salt bead, while hot, for copper it will be green, for nickel 2+ it will be violet, and for Fe 3+ it will be yellowish brown. Another preliminary test we usually perform is the charcoal cavity test. Metallic salts, when heated with anhydrous sodium carbonate in a charcoal cavity, decomposes to give the corresponding oxide with the characteristic color. Sometimes the oxide may be reduced to metal by the carbon of the charcoal cavity. From the color of the residue, the metal ion can be identified. Charcoal cavity is a block of charcoal having a cavity on it. About 0.2 gram of the salt is mixed with thrice the weight of anhydrous sodium carbonate and fill the cavity with it. Moisten the mixture with 1 or 2 drops of water, otherwise the mixture will blow away. Make a luminous flame in the Bunsen burner by completely closing the air holes. Place the pipe near the bottom of the flame and blow air through it. The flame bent towards the cavity and heat the mixture in the cavity. If we have taken copper sulfate, it will be converted to copper carbonate at first. On further heating, copper carbonate decomposes and a copper oxide is formed. The copper oxide formed get reduced to metallic copper, which appears as a red colored residue in the cavity. When we use zinc sulfate, it first converted to zinc carbonate and then to zinc oxide. The residue will be yellow when hot and white when cold. The table shows the color of the residue and the inference that we can arrive at. When the residue is yellow while it is hot and grey metal when cold, it indicates Pb2 plus ions. White residue with the smell of garlic indicate arsenic ions. Red color indicate copper ions. Brown residue indicate cadmium. Yellow residue when hot and white when cold indicate zinc. When the residue obtained in the charcoal cavity is white, we perform the following tests. The residue is mixed with 2 or 3 drops of cobalt nitrate solution and strongly heated in a non-luminous flame with the help of blowpipe. On heating, cobalt nitrate decomposes into cobalt 2 oxide and gives a characteristic color with the metal oxide taken in the cavity. Cobalt nitrate decomposes to cobalt oxide. When zinc oxide is taken, it forms a green mixture. And if it is magnesium oxide, we get a pink mixture. And if it is aluminum oxide, we get a blue mixture. From this slide onwards, we will discuss the wet test for identification of cations. The detection of cations is based on their ability to form insoluble salts such as chlorides, sulfides, hydroxide, carbonates, etc. The precipitation of these salts depends on the solubility and the solubility product principle. By considering the solubility and solubility products of these salts, we devise a scheme for the analysis of cations by converting them into insoluble salts. For the convenience of analysis, we classify the cations into different groups. The following table shows only the cations we need to study. In fact, each group includes cations other than that shown here. Group 0 is ammonium and no general group reagent is there. Group 1, lead 2 plus, the group reagent is dilute HCl. Group 2 contains lead 2 plus and copper 2 plus, and the group reagent is H2S in presence of dilute HCl. Group 3 include aluminum 3 plus and Fe3 plus, and H4OH in presence of ammonium chloride is the group reagent. Group 4, zinc 2 plus and nickel 2 plus, and here the group reagent is H2S in presence of ammonium hydroxide. Group 5, barium 2 plus and calcium 2 plus, ammonium carbonate in presence of ammonium hydroxide. Group 6, magnesium, no special group reagent is there. This is because magnesium also includes some other cations, and for each cations we use a separate reagent characteristic of it. As I said before, all the groups contains several other cations. For example, group 4, it includes manganese and cobalt also. We need to study the principles behind the detection of these cations only. The first step in wet test is the preparation of original solution. We use solvents in the following order. First we use water. If insoluble in water, we use dilute HCl, and still it is insoluble, we heat the solution. And even if it is insoluble after heating, we use concentrated HCl and heat, then dilute HNO3, and if the salt is insoluble in all these solvents. Then we use aqua regia. It is a mixture of concentrated HCl and HNO3 in 3:1 ratio. But here we need to study only water soluble salts. Moreover, the salts will contain only one anion and one cation. That makes our analysis very simple. We perform various tests using original solution. And this is the original solution we prepare and we keep it in a boiling tube as a stock solution. The zero group cation ammonium plus is analyzed separately. We start with ammonia ion which comes under the zero group. For zero group, we use the given salt. So take about 0.1 gram of the salt in a test tube and add 1 to 2 ml of sodium hydroxide and gently warm the solution. The salt dissolves. If the solution smells ammonia, the presence of ammonium ion is indicated. So we try to find out the smell of the gas evolved. So if it smells ammonia, that shows the presence of ammonium ion. This figure is shown only as a symbol for detecting the smell. In the laboratory, never smell any gas directly from the test tube. Fan the gas towards your nose, keeping the test tube away. Now we again gently warm the solution. So some fumes are coming out. Now place a glass rod dipped in hydrochloric acid near the mouth of the test tube. So white fumes are observed. And these white fumes are due to the formation of ammonium chloride vapor. So if the given salt is ammonium sulfate, when we heat it with the sodium hydroxide, ammonia gas is produced. This is the ammonia gas produced and it combines with the HCl vapors so that ammonium chloride vapors are produced. The second test for ammonia ion is we pass the gas that is produced when it is heated with the sodium hydroxide into Nessler's reagent. A brown precipitate is obtained. And this brown precipitate is due to the formation of this complex. Nessler's reagent is this one, K2HgI4, and it combines with the ammonia in presence of potassium hydroxide or sodium hydroxide. We get this complex, that is basic mercury 2 amido iodine, and this is brown in color. We can devise a flowchart for the detection of the cation present in the given salt. This flowchart is useful when there is only one cation to be detected. First we start with the original solution. To that we are adding dilute HCl. If a precipitate is formed that indicate group 1 cation, that is lead 2 plus, and a lead 2 plus will be precipitated as lead chloride. And if no precipitate is formed, we pass hydrogen sulfide gas through the solution. If a precipitate is obtained, that indicate the presence of group 2 cations. These are lead and copper 2 plus. Usually lead may not be completely precipitated in group 1. So therefore group cation may also be, lead may also be precipitated in group 2. And here the lead and copper are precipitated as sulfides. If there is no precipitate, then we take the original solution and add ammonium chloride and ammonium hydroxide in excess. If a precipitate is obtained, we can infer the presence of group 3, that is Fe3 plus or Al3 plus as hydroxides. If no precipitate is formed, we pass hydrogen sulfide gas through this solution, and if a precipitate is obtained, that shows the presence of group 4. And this may be either zinc 2 plus or nickel 2 plus as their sulfides. If no precipitate is obtained, then to the original solution, not this one, to the original solution add ammonium hydroxide and ammonium carbonate. If a precipitate is formed, it will be group 5. It may be barium or calcium, and these are precipitated as carbonates. And suppose that there is no precipitate, then we test for group 6. Group 6 is magnesium. And there is no common group reagent, and separate reagents are used for magnesium and other ions that comes under group 6. First we consider the analysis of group 1 cation, and that is lead 2 plus. And when dilute HCl is added to the original solution, a white precipitate is obtained, and this is due to the formation of lead chloride. Now we heat the solution, it disappears. That is, lead chloride is soluble in hot water. Now we divide this solution into 3 parts in 3 test tubes. To the first part, we add potassium iodide solution. An yellow precipitate is obtained, and this yellow precipitate is due to the formation of lead iodide. So the solution contains lead chloride, and potassium iodide is added, lead iodide is precipitated. And to the second part we add potassium chromate solution, and here also we get an yellow precipitate, and this yellow precipitate is due to the presence of lead chromate. Lead chloride plus potassium chromate, we get lead chromate, which is yellow in color. But this lead chromate will dissolve in sodium hydroxide by the formation of this complex. And this complex is soluble. That is why lead chromate dissolves in sodium hydroxide. Next, to the third portion, we add dilute sulfuric acid. A white precipitate is obtained. The white precipitate is due to the formation of lead sulfate. And when you add ammonium acetate to the solution, it dissolves, and due to the formation of this complex. Since we will be given only one cation, if a lead is absent, we go for copper 2 plus. When lead is absent, we can use the same solution that is used for testing group 1, since it contains HCl. The group reagent is dilute HCl and hydrogen sulfide gas. Dilute the solution by adding water and pass hydrogen sulfide gas from the Gibbs apparatus. When we open the stopcock, hydrogen sulfide gas will come out through the tube, and the acid from the bottom will go up, and it comes in contact with this is ferrous sulfide, and more hydrogen sulfide will be produced. When the stopcock is closed, the acid move down, and there is no contact between ferrous sulfide and acid, and no hydrogen sulfide will be produced. Now I am turning on the stopcock. We are bubbling hydrogen sulfide gas through the solution. A black precipitate is formed, and this black precipitate is due to the formation of copper sulfide. Now we remove the test tube, and we are adding dilute nitric acid to the solution, and boil the solution. The precipitate dissolves, and this is due to the formation of copper nitrate, and this is the reaction copper sulfate. Sulfur also will be precipitated here. If you go on heating the solution for a long time, the solution turns blue, and this is due to the oxidation of sulfur to sulfate by nitric acid. And copper 2 plus and sulfate gives copper sulfate. And copper sulfate is blue in color. And the blue color here is due to the presence of copper sulfate. We add a few drops of acetic acid and potassium ferrocyanide, and we obtain a chocolate brown precipitate. And a chocolate brown precipitate is due to the formation of copper ferrocyanide. Copper sulfate plus potassium ferrocyanide, we get copper ferrocyanide. And potassium ferrocyanide is potassium hexacyanoferrate 2. And copper hexacyanoferrate 2, that is copper ferrocyanide. And this complex is having a chocolate brown color. If group 2 is absent, we go for group 3 cations. These are Fe3 plus and aluminium 3 plus. The group reagent for is solid ammonium chloride and ammonium hydroxide in excess. Therefore, we have to take the original solution because the previous solution cannot be used here. It contains hydrogen sulfide. About 2 ml of the original solution is taken, and to that we are adding a few drops of concentrated HNO3. And this is to oxidize the ferrous ions to ferric ion if present. Heat the solution for a few minutes. And after cooling, a small amount of ammonium chloride, this is solid ammonium chloride, is added, and then excess of ammonium hydroxide solution is added. Ammonium hydroxide in excess. Ammonium hydroxide in excess means that the solution should smell ammonia. Shake the test tube well, and 2 observations are possible here. Either we will get a brown precipitate or a white precipitate. The brown precipitate shows the presence of ferric ion, and the white precipitate shows the presence of aluminum. Ferric ion is present as ferric hydroxide, and aluminum is present as aluminum hydroxide. We take the brown precipitate first. It is ferric hydroxide. Now dissolve the brown precipitate in dilute HCl, and we divide it into 2 portions. That is ferric hydroxide dissolved in dilute HCl giving ferric chloride. But this solution contains ferric chloride. To the first portion, we add potassium ferrocyanide. Potassium ferrocyanide solution. A blue precipitate is formed. If excess potassium ferrocyanide is added, a colloidal solution called soluble Prussian blue forms, and the solution becomes blue in color. So ferric chloride, potassium ferrocyanide, and this complex is Prussian blue. It is iron 3 hexacyanidoferrate 2. To the second part, we add potassium thiocyanate. And when potassium thiocyanate is added, an intense red color, which is called a blood red color, appears. And this is due to the formation of ferric thiocyanate. So the solution contains ferric chloride, and potassium thiocyanate contains thiocyanate ion, and we get ferric thiocyanate, which is blood red in color. If no brown precipitate is obtained in group 3, we can infer that ferric ion is absent. And if instead a white precipitate is obtained, that shows the presence of aluminium. The white precipitate appears as gelatinous white precipitate, and that is due to the formation of aluminium hydroxide. We dissolve the precipitate in dilute HCl. The hydroxide is converted to chloride, and now we keep a portion of the solution for another test. To the first part, add sodium hydroxide solution and warm. A white gelatinous precipitate is formed, and this is due to the formation of aluminum hydroxide. Now we add excess sodium hydroxide to the solution, and the precipitate get dissolved, and this is due to the formation of sodium aluminate. When sodium hydroxide is in excess, it is converted to aluminum hydroxide is converted to sodium aluminate, and that is soluble. Now we take the second portion. To the second portion, we add blue litmus solution. A red color appears, and this is because this solution is acidic in nature. And now we add ammonium hydroxide drop by drop through the sides of the test tube. The solution becomes alkaline, and aluminum hydroxide is precipitated. The precipitated aluminum hydroxide absorbs the blue color from the litmus solution and forms insoluble adsorption complex. And this is usually called a lake. Thus, a blue mass floating in the colorless solution is obtained. This test is called the lake test. The appearance and the color shown in the animation may not match exactly with the color and appearance when you do the experiment actually in the laboratory. The purpose of animation is to make you understand the concept behind the experiment. The fourth group cations are precipitated as their sulfides. Even though the fourth group contain or include zinc, manganese, nickel and cobalt, we need study only zinc and nickel. The group reagent is ammonium chloride, ammonium hydroxide in excess, and hydrogen sulfide gas. If group 3 cations are absent, the solution contains ammonium chloride and ammonium hydroxide in excess. So we need pass only hydrogen sulfide through the solution. And for that we use a Gibbs apparatus, and we pass hydrogen sulfide gas through the solution. Two observations are there: either a black precipitate or a white precipitate is obtained. The white precipitate is due to the formation of zinc sulfide, which is white, and the black precipitate is due to the formation of nickel sulfide, and that is black in color. Now we take the white precipitate and we dissolve it in dilute HCl by boiling. Now we divide this solution into two portions. To the first portion, we add sodium hydroxide. A white precipitate is formed. Further addition of sodium hydroxide dissolves the precipitate. If you add more sodium hydroxide, the precipitate dissolves. And this confirms the presence of zinc. Zinc sulfide, when dissolved in HCl, it is converted to zinc chloride. And when sodium hydroxide is added in excess, it is converted to sodium zincate, and this is soluble. Now we consider the second portion. And we neutralize the second portion with ammonium hydroxide and add potassium ferrocyanide solution. This is potassium ferrocyanide. Now a bluish white precipitate appears, And the bluish white precipitate is due to the formation of zinc ferrocyanide. And the zinc ferrocyanide is bluish white in color. If instead of a white precipitate, we get a black precipitate, it indicates the presence of nickel or cobalt, because both the nickel sulfide and the cobalt sulfide are black in color. But we need study only nickel. So we take this solution and to that we are adding aqua regia. Aqua regia is 1:3 concentrated HNO3 and concentrated HCl. Now we take this solution and heat it to dryness. So this is nickel chloride. We dissolve the residue in water and take a portion of it. And we neutralize it using ammonium hydroxide or made it alkaline. And to that solution we are adding dimethyl glyoxine. And a bright red precipitate is formed. And this bright red precipitate is due to the formation of nickel dimethyl glyoxide. The formation of red precipitate confirms the presence of nickel. The reaction can be represented like this. So when you dissolve the precipitate in aqua regia, we get nickel chloride. Then alkaline, made alkaline by ammonium hydroxide. And this is dimethyl glyoxine, a bidentate ligand. And this is the complex formed. That is nickel dimethyl glyoxine. We now move to group 5 cations, barium and calcium. It also includes strontium, but we need study only barium and calcium. If group 4 is absent and we take a little of the original solution, this is because the group reagent is ammonium chloride and ammonium hydroxide in excess and ammonium carbonate. We cannot use the previous solution because it contains hydrogen sulfide. And this is ammonium chloride solid. We add some of the solid ammonium chloride into the solution. Now we add excess of ammonium hydroxide. And to that solution, we add solid ammonium carbonate. This is solid ammonium carbonate, and a little sodium solid ammonium carbonate is added to the solution. A white precipitate is formed. And this is due to the formation of either barium carbonate or calcium carbonate. If the given salt contains barium, this will be barium carbonate. If the given salt is calcium, this will be calcium carbonate. Now we take the precipitate, separate the precipitate, and keep a small portion of the precipitate for doing the flame test. Now we dissolve this precipitate, group 5 precipitate, in acetic acid so that it is converted to the acetate. So we boil the solution and it gets dissolved. We divide the solution into 2 portions, and these solutions are either barium acetate or calcium acetate because we dissolve it in acetic acid. If the given salt is contain barium, this will be barium acetate, and if it is calcium, it will be calcium acetate. To one part of the solution from the previous experiment, we add potassium dichromate solution. So that is either, this is the first part. And if an yellow precipitate is formed, that shows the presence of barium. That is, the yellow precipitate is barium chromate. Therefore, the solution contains barium acetate. When we add potassium chromate, barium chromate precipitates. Now we take a small portion of the group 5 precipitate we placed earlier, and we use that precipitate to do the flame test. For that, we need to make a paste using concentrated HCl, and using a platinum loop, we introduce a little of the paste into the flame. So we get a green, apple green, or a can be called grassy green flame. And this grassy green flame confirms the presence of barium. If barium 2 plus is absent, we do the test for calcium. To the solution of the fifth group precipitate in acetic acid, we add ammonium oxalate solution. So this is the fifth group precipitate dissolved in acetic acid. And if we get a white precipitate, that shows the presence of calcium. The solution we have taken is, that is, when we dissolve the fifth group precipitate in acetic acid, we get calcium acetate, and from this we get calcium oxalate. And now we do the flame test using a small portion of the group 5 precipitate, and we dissolve the precipitate. We make a paste using 1 or 2 drops of concentrated HCl and introduce into a non-luminous flame. And this is brick red color, and the brick red flame indicate or confirms the presence of calcium. If none of the above tests are answered, we go for group 6. Group 6 contain magnesium 2 plus. Group 6 also includes sodium plus and potassium plus, but we need consider only magnesium 2 plus. There is no common reagent for this group, and the cations are identified by test characteristic of each ion. In group 5, we are adding ammonium carbonate. Therefore, if group 5 cations are absent and if magnesium is present, we expect magnesium carbonate to be precipitated. But this does not happen. The presence of ammonium plus ions reduce the concentration of carbonate ion in this solution, and which prevent the precipitation of magnesium carbonate. The reagent used for detecting magnesium ion is disodium hydrogen phosphate. And to the solution obtained from group 5, or we can use original solution plus ammonium hydroxide and ammonium chloride, we add disodium hydrogen phosphate solution. Disodium hydrogen phosphate solution. Now precipitate appears. So we scratch the inner side of the test tube by a glass tube. A precipitate appears. A white precipitate appears. And this confirms the presence of magnesium 2 plus. The scratching using glass rod is to initiate the precipitation. That is, if group 5 cation is absent, the given salt contain magnesium, it will be present as magnesium carbonate in the solution. Magnesium carbonate will not be precipitated because the concentration of carbonate ion is not sufficient to overcome the solubility product of magnesium carbonate. This is because of the following equilibrium, and this equilibrium is always shifted towards the right. That is, excess ammonium ions are there, so therefore it is shifted towards the right, and that will reduce the concentration of carbonate ions. When disodium hydrogen phosphate solution is added and the inner sides of the test tube is scratched with a glass rod, white precipitate of magnesium ammonium phosphate separates. This is magnesium ion, disodium hydrogen phosphate. We get magnesium ammonium phosphate and sodium sulfate is formed. The scratching provides the nucleation sites. and which are small solid surfaces formed by chipped off microscopic glass pieces, where solute molecules can gather and form solid crystals. So scratching the inner side of the test tube initiate precipitation.